Welcome students to your video on direct variation. We say that when two things vary directly, they are proportional, and you can use proportions in order to solve problems with direct variations, but you can also use a simple equation, and we're going to jump in and start talking about that right now. Okay, so in a direct variation, you're going to use x and y. As x increases, y also increases, and we're going to consider a simple situation. The standard shower head puts out 3 gallons of water each minute during a shower. The amount of water used in a shower varies directly with the number of hours the shower has been running. So, you read that right, and it may have shocked you, but 3 gallons per minute. So let's make a little table of values, and we're going to use x and y. And what we say with a direct variation is that x varies, x is proportional to y is proportional to x, y varies with x. So y changes as x changes. So let's make x our number of minutes, and we'll make y our gallons of water. All right, and let's think about this from a step-by-step perspective here. How about no minutes at all? You don't use any water. A 1 minute shower, 3 gallons of water. Now let's be realistic here. The minimum amount of time that you're spending in there is probably 5 minutes. And that would be 15 gallons. More of you are probably spending more like 10 minutes. That'd be 30 gallons. Some of you are probably spending 20 minutes. That would be 60 gallons. And I bet even some of you are spending 30 minutes in there every day. Now I want you just to think about this just for a minute. I want you to think about 1 gallon. Most of you probably have 1 gallon of milk sitting in your refrigerator, right? 1 gallon. Now, let's think about that size. Okay, that's the best I can do. I know it's not a brilliant drawing, but you catch my drift. Let's think about that size. Let's think about 90 of those, all lined up for a 30-minute shower. I hope some of you may rethink the amount of time you're spending in that shower. Anyway, this is a direct variation. As x is increasing, y is also increasing. And we can actually write a very simple equation for this. We can write it as y equals something happening to x. And what happens to x in order to get y? It's being multiplied by 3. Y equals 3x. So let's look at some definitions. Two sets of data have a direct variation if they are related by a constant ratio called the constant of proportionality or the constant of variation. Constant of variation. The graph of the data sets is linear, makes a line, and always passes through 0, 0. And it's easy to see why it always passes through 0, 0 if you look at the basic equation of a direct variation. See that right here. Y equals k times x. And k represents that constant of variation that we were just talking about, or constant of proportionality. I usually say k for constant, which is just terrible. But that's the variable they chose to use. In that direct variation, k is a constant. And it says here k is a constant ratio. And what we mean by that is if you look at this equation here, y equals k times x, and if I solve it for k by dividing by x on each side, I get y over x is equal to k. The ratio of y to x is k constant. So that is the relationship in any direct variation situation. The ratio of y to x, the output to the input, will always be the same. To determine whether two sets have direct variation, you compare the ratios. You can also graph the data sets on a coordinate grid. So graphing is a great way to tell if you have a direct variation, although we should definitely be able to do it without having to get a sheet of graph paper. So you can see this particular direct variation here. X is equal to 3, y is 15. When x is 5, y is 25. And when x is 8, y is 40. And you're probably very quickly recognizing the relationship there. But in order to show whether or not this is a direct variation, the best thing to do is to start by finding the ratios of y to x. And you can see those listed right out here. And in every single circumstance, the ratio is the same, 5 to 1. So it is a constant ratio. That means that that constant of variation is 5, and we can write this equation y equals 5x. The graph of the data sets is linear, and you can see that over here on this graph. Goes through 0, 0, and this definitely does show a direct variation. So in order to tell if you have a direct variation circumstance here, you're going to divide y divided by x and see whether or not it is k for constant. All right, so let's take these two for example. All right, so here we have 1, 2, 4, and 8 as x values, 8, 4, 2, and 1 as y values. And the ratio here, 8 to 1 is 8, 4 to 2 is 2. So we do indeed not have a constant ratio. Okay, we don't need an equation. Is the graph linear? Well, let's take a second to graph it. 1, 8 would be here. 4, 2, 2, 4 would be here. 4, 2 is there. And 8, 1 is here. And that is definitely not a linear graph. That is actually something we're going to see in a coming video called an inverse variation. No, definitely not a linear graph. That'll be there. We'll be talking about that. We'll be there very soon. So don't stress about that. Just know, not a direct variation. All right, how about this one? Is the ratio constant? So let's do this one. 0 divided by 0. Well, that's, you can't divide 0 by 0, so let's keep going. 20 divided by 2, that's 10. 30 divided by 3, that's 10. And 50 divided by 5, that is 10. So the constant of variation here is 10. Yes, we have a constant ratio. If yes, the equation. So in order to give the equation, we're going to write it as y equals, and the k value times x. Is the graph linear? So let's graph it 0, 0, 220, 330, 440, 550. And is that linear? Whoop. Get the right tool. Yep. Wrong color there, but yes, the right tool. So yes, this is a linear graph. So yes. So that one was a direct variation. All right. Let's take a look at the next one. Okay, so I want you to try these couple on your own. I want you to use the method we just used for the tables for the first three. And then when it comes to the equations, I want you to think about the formula that you just learned, y equals kx. Do they fit? Can you write them in that manner? All right, take a look, figure it out, and then come back and watch as I walk you through all 5. Okay, I'm going to start with this one up here. So we're looking at ratios. -2 to 0, we can't actually find. 1 to 1, we get a 1. 4 to 2, we get 2. And 7 to 3 is 7/3. So no, this is not a direct variation. Definitely not. Because again, we're looking at the ratio of y to x. Next one, 4 to 1 is 4. 8 to 2 is 4. 12 to 3 is 4. And 16 to 4 is 4. Yes, this is a direct variation. You've got a constant of variation of 4. And we can even write the equation, y equals 4x. Okay, next one, 4 to 2. 4 to -2, excuse me, is -2. 2 to -1, -2. 0 to 0, we can't really find that. And 2 to 1 is 2. So again, we have a similar ratio, but it's not exactly the same. And therefore, this is not a direct variation. All right, how about the next 3? We're looking at whether or not the equation can match a direct variation. Can we write this equation right here, xy equals 3, can we write that in that form y equals kx? Well, let's solve for y. And in solving for y, we get y equals 3 over x. This is definitely not a direct variation. In fact, that is again something we're going to learn in the next video called an inverse variation. All right, next one. Can we write this as y equals k times x? We sure can, because if we multiply both sides by 3, we get 3x equals y, or y equals 3x. And that is indeed a direct variation. So that one is, yes, definitely. And what about this one? Again, we can solve for y, and we get y equals x minus 1, but that is not a direct variation. because you have a circumstance that is not k times x, it's x minus 1. It's a basic linear relationship, but it is not a direct variation. Okay, kids, thanks for watching. We're going to move from direct variations to inverse variations. But go back, make sure you have quality notes for this one. I will see you guys in class.